Question number 10 is about the rate of thermal energy transfer. So basically, we need to use this equation, and you got it right. That's good. We have two windows here. Window 1 is made of a single glass pane of thickness D, and window 2 is made of two glass panes of thickness D, each separated by a thin air space. Both windows have the same surface area, so it's the same A, and separated air masses of the same temperature difference. So basically, we have two scenarios. This is the first case for the window 1 with the temperatures between T1 and T2. Let's assume that T1 is hotter than T2, so we can have the heat being transferred from the outside to the inside. And this is the thickness of the glass layer, like D. So basically, we can just apply this equation and we can have this one. Where this one is the thermal conductivity of the glass, the materials. So if we have the scenario number 2, there will be different layers. So we actually have 3 different layers here. We have the first layers of glass also from T1 at first, then go through the layer of glass. It will drop to some TR1, and we just kind of like exaggerate the space of thickness in between so that we can see clearly there's a difference between the temperature here right after the first layers of the glass and right here right before the second glass layer, and then it reached the final T2. There should be the same T2 and the same T1 based on the problem statement. Okay, so now they just ask us to compare the thermal energy transfer in this case and how is it compared to the first one. So actually here the keyword is that thermal energy transfer in the unit time is Q. So basically the whole thing here, this means that a Q per unit time. So the Q itself here should be in which unit? It should be in watts, right? Yes. So basically it should be in rate, in the unit of watt, because that will be joule in second. For example, if we have the unit of time in seconds, then it should be watt, like the unit for the power. Okay, so how can we solve this problem? At first, if we think about this one, like, okay, we can have a amount of thermal energy transfer through this layer, another through this layer, and another through this layer. So actually, we can have the Q class 1 over the first time for the temperature, for the flow, a heat flow go through this one, right? So that should be the T, the delta T1. This is the time, the time amount to cross the first layer. And then the same we have, this is like the amount of thermal energy, the heat through the air. And this is also the time through the second layer. And that's also like the last one through the second class layer. And this is the time to travel through it. So actually, I want to highlight that if we cannot distinguish clearly between this one is like the rate, okay, the rate of thermal energy transfer through the first layer. So there's a difference here. This is the total heat. So this is the sum of total heat. And this is the total time. This is the total sum of the time. Okay, so they different, right? You have, this is a ratio, the fraction of all of them summed together and over another sum, which will be different from the sum of each of the ratio, right? Just mathematically. So that's why if you just happen to substitute this one to be this one, and then this one to be this one, and then if you just mistakenly take this one as like plus here addition, that's not correct. Okay, why? Because actually if you got the amount of heat go through this one, we kind of assume that the rate should be the same. So the rate that travel through the first layer is the same with the rate travel through the second layers, and is the same with the rate travel through the third layer. So imagine if you got these two equal to each other, if you use this expression, then you got it's just like one rate, twice of the rate, and then 3 times of the rate. So then you got in the end, oh, the rate itself equals to 3 times of it, which doesn't make sense. So that's why, remember, don't use this equation. This is not correct, okay? But the heart of this one is that they're all the same rate, that the same rate of thermal energy transfer. So this one kind of similar to like the problems with resistance, electrical resistance in series. So you can have a look at it like this. If you have the same rate, so that should be like the same, it kind of interesting that in electricity, you also have intensity or like the current, right, equals to Q over delta T, right? But Q over that is like the charge over the time. I just want to point out because it's kind of similar. So that would be the same rate, or it would just like be the same current. That would be the same current travel through each layer. But in this case, this is not electrical current, but it's like thermal, okay, thermal energy current. You got a flow of energy going through each layer, okay? So same current, okay? Same rate, okay? So if it's the same rate, then just imagine if you go through the first layer, it has some drop of the first delta T, and then it keep having another drop, the second drop, and then you have another third drop in temperature. So basically, if we add all of them together, you can see that this one can be treated as layers as thermal resistances in series. So then we have a new concept, the thermal resistance. So basically, how can we calculate the thermal resistance? You can get the thickness. Okay. Oh, we don't have any A's in here. This is just a typo. Okay. So if you just have a look at this one, this is like the amount of heat transfer in a unit of time. So this is the rate equals to, this is the change in temperature, right? Okay. And just simplify everything, we just like combine all the things here to make it a resistance. And we want to say that, okay, the rate, if you remember about the Coulomb's law in electrical circuit, you have the rate equals to the voltage drop, the difference between potential over resistance, right? Okay, so you can see this is also like this kind of the same rate. This is also the same rate, and then this is like the drop in temperature. This is just like the drop in voltage. Then you got this one is like the resistance. Okay, but this one will be the thermal resistance. Make sense, right? This one is kind of similar to this one in electricity. So I will just put it here. This is related to electrical circuit. But this concept will be helpful for us to apply in this case. Okay, so basically you got the rate equals to the total drop in temperature over the R as the thermal resistance, and basically the whole thing here equals to R, or like R will equal to the thickness over the conductivity and area. So this is the thermal resistance. So if we want to find the total resistance, we just add them together through different layers. So that's why here in this case, for the second scenario, we can see that it will be the same change in the temperature between the very initial and the final one, right? So now we have in the first case here, that will be also the same change. So this is like the Q1 over delta T1. So this is the rate in the first scenario, and this is the resistance over the resistance R1, right? So this is the whole thing here. Now let's just apply this one for the second case. We might have some total Q2 travel through the whole system. Okay, I don't care like how much is changed here, how much is changed here, how much is changed here. I just care the total as Q2. Okay, and then there will be also like over the same time, and now we just have the total resistance, thermal energy resistance. So this would be like the D of the class over the K of the class and the surface area, cross-sectional surface area of this one. And then this one will be the dA here, the Ka, the K of the air, and also the surface area, and it's also the same A, and then the last one like this. So if you compare these terms and these, you can see that the whole things here equals to the sum of all the three terms here, and 1, 2, 3 terms here. So if we just want to pick out these two terms here, we add them together, that will be like the 2 of the D class, right? This is like make it to be 2. And because this whole thing here also included another terms, and this one is also positive, so it's clearly that the whole things here will be greater than just this one added with this one, right? That's why we can have this relationship. And from here we can just simplify. We have the class C, class K, class A the same, so we just have the 2 here. So if we divide both sides for number 2, then we got this one. And this one turns out that this is the rate of the first K is Q, and then this one is the second K, so that's why it's less than half of it. So that's why our answer is A, less than Q over 2. Okay, if you have any question, please let me know. So basically, remember, for this problem, we cannot apply this equation, right? This is not correct. Because why? Because we have the same rate, and same rate mean that each of this equals to each other to make sure that the heat kind of flow evenly through our layers. It just turns out that if the K of the air and the D of the air is different, then the temperature drop will be different compared to when it goes through the glass. Okay, yeah, and just apply it just like in the electrical circuit problems for series. Okay, just like you find the R equivalent, and then instead of having the difference in potential, you use the difference in temperature. Okay, please let me know if you have any question. Thank you.